Okay, let's dive right into this explainer and uncover how British physicist Paul Dirac successfully united the two greatest pillars of physics and, completely by accident, discovered half the universe along the way. We're going to look at one of the most stunning triumphs of theoretical physics, where pure mathematics actually predicted reality long before our instruments ever could.
Some physicists have referred to the Dirac equation simply as the real seed of modern physics. But how exactly did one guy sitting with a pencil in 1928 accidentally stumble onto a purely mathematical structure that so profoundly rewrote our understanding of reality? Well, to really appreciate the magnitude of this, we have to look at the exact moment in history when it all went down.
Section 1. Physics in Crisis and the 1927 Roadblock.
To understand Dirac's monumental breakthrough, we first have to look at the frantic, almost crisis-level pace of physics in the 1920s. This incredibly condensed, rapid-fire timeline shows brilliant minds just racing to understand the ultra-small. In 1925, Heisenberg, Born, and Jordan gave us matrix mechanics. The very next year, Schrödinger gave us his famous wave equation, while others worked out the Klein-Gordon equation. By 1927, Wolfgang Pauli introduced the concept of spin. It was this explosive era of discovery, right? But despite having all that absolute genius in one room, they were about to hit a massive, fundamental roadblock.
And the core problem was this. Physicists simply couldn't get the mathematical rules of the ultra-small to play nicely with the rules of the ultra-fast. Early quantum mechanics worked beautifully for tiny particles, but it completely fell apart if those particles moved anywhere near the speed of light. Meanwhile, on the flip side, Einstein's special relativity handled light speed perfectly, but it totally clashed with the probabilistic nature of quantum mechanics. Previous attempts to combine them, like the Klein-Gordon equation, required a second temporal derivative, which unfortunately just ruined the probabilities that quantum mechanics desperately relied on. Honestly, it seemed completely impossible to merge the two.
Section 2. Uniting the two frameworks, the ultimate bridge.
In 1928, Dirac strongly objected to the messy compromises and ad hoc modifications other physicists were making just to force their math to work. He wanted a true, first principles, relativistic theory for the electron. So his crucial point was this radical leap to linearize his equations. Basically, he needed an equation with only a first derivative in time, just like Schrödinger's, but it also had to satisfy Einstein's relativity. To do this, he had to take the square root of a highly complex momentum operator. Dirac quickly found he couldn't do this with standard numbers. Not even the 2x2 matrices Wolfgang Pauli had used were enough. Instead, he realized he absolutely had to use four-dimensional matrices.
Now, what's truly fascinating here is that Dirac didn't introduce these four components based on some physical observation from a laboratory. Not at all. He introduced these four-component wave functions, which we now call Dirac spinors, as a matter of pure mathematical necessity. Two of the components neatly explain the known spin states of the electron, spin up and spin down. But the math demanded two additional totally mysterious states. Dirac had no idea what they were for yet, but he trusted the math.
Section 3. The antimatter surprise, a bug turned feature. Let's look at the immediate aftermath of his 1928 paper, because this builds into one of the greatest plot twists in scientific history. Right out of the gate, the equation was an absolute triumph from first principles. It immediately succeeded where every previous attempt had failed. It natively predicted the electron spin of 1/2, without anyone having to manually plug it in. It perfectly reproduced the fine structure of the hydrogen atom, and correctly described complex particle interactions like Klein-Nishina and Mott scattering.
It seemed like the perfect, ultimate solution for relativistic quantum mechanics. It was elegant, it was effective, but lurking deep in the math was a profound anomaly. The equation predicted something no one was looking for, and frankly, something no one even thought was possible.
Remember those two extra components in his four-dimensional matrices? Well, they represented negative energy states. In 1929, physicist Oscar Klein pointed out that Dirac's equation inevitably mixed positive and negative energy states together. This was seen as a massive mathematical bug. Initially, even Dirac himself thought it meant his equation was defective, that maybe it was just a first approximation of some future better theory. Because, after all, what does an electron with negative energy even look like?
At first, physicists just tried to reject these negative energy states as unphysical defects, but the math wouldn't allow it. So to solve this, Dirac proposed the Dirac sea. He imagined that the vacuum of the universe isn't actually empty, but is instead filled with an infinite sea of negative energy electrons.
Fully trusting this wild mathematical framework, in 1931, he theorized that a hole in this sea would look exactly like a particle with the same mass as an electron, but with a positive charge. He called it an anti-electron. And just 2 years later, in 1933, Carl Anderson proved him right, experimentally discovering the positron. Just by trusting the math, Dirac turned a glaring bug into a feature, predicting the existence of antimatter before a single piece of it was ever observed.
Section 4. Inside the math. Formulating the universe.
Let's take a quick look under the hood to see how this incredibly robust mathematical formulation actually works. The real elegance of the Dirac equation is its foundational flexibility. It governs Dirac fermions, massive particles like electrons and quarks. But if you apply a limit of zero mass, the equation neatly decomposes into Weil equations, which describe massless left or right-handed particles. Or, if you use a purely real mathematical representation, you get Majorana spinors, particles that act as their own antiparticles. The Dirac equation isn't just one solution, it's literally the parent architecture for describing spin 1/2 particles across the entire universe.
These key properties explicitly show why he was so successful. By remaining invariant under Lorentz transformations, he satisfied special relativity. By keeping the equation linear in temporal derivatives, he satisfied the probabilistic rules of quantum mechanics. And by generating his famous 4x4 gamma matrices, which form a neat geometric mathematical structure known as a Clifford algebra, he seamlessly integrated the probabilistic rules of quantum mechanics right into the physical geometry of space-time itself.
Section 5. Seed of modern physics. The legacy of 1928.
So you might be wondering, why does a highly theoretical equation formulated on a piece of paper nearly a century ago matter so much to you and me today? Well, because the device you're using to view this explainer right now exists in a universe governed by the standard model of particle physics, which inherently relies on Dirac's framework. His equation forms the absolute bedrock of quantum electrodynamics. But it's not just abstract particle physics either. Today, in condensed matter physics, researchers use the exact principles of the Dirac equation to understand Dirac matter. This includes wonder materials like graphene and cutting-edge topological insulators that are actively shaping the future of electronics and quantum computing.
It's almost entirely unprecedented in the history of science. How is a purely mathematical structure, discovered on a chalkboard in 1928 just to solve an annoying physics roadblock, currently being used to engineer tomorrow's graphene technologies? It leaves us with this profound realization. Paul Dirac didn't just solve a puzzle of the ultra-small and ultra-fast. By trusting the pure abstract mathematics staring back at him, he literally handed us the blueprint to manipulate the very fabric of our modern world. And honestly, it makes you wonder, what other mathematical anomalies are sitting on a chalkboard right now, just waiting to unlock the other half of our universe?